Good morning. So today we will continue our discussion on the same topic or same module, that is materials for energy storage and devices. In the previous lecture, I gave an idea about what are the storage devices which are presently in use in order to store energy and for various applications. So three different devices which I introduced in my previous lecture are battery, capacitor, supercapacitor and fuel cell. If I just go back to the to my previous lecture and try to see what is the importance of to make these devices storage devices, are that one needs a good set of storage device with good efficiency, with reliability, with better temporal stability and with good power and energy. So these are the main objective to make a good storage device. So as I mentioned in my previous lecture, these batteries are some devices which we regularly see. These are used in many applications and also household appliances. So everybody knows about battery. And then I talked about capacitor. And this is also a very known device, well-known device, because we all use capacitors, be it in the laboratory or household appliances. So you all know when we talk about capacitor, how does it look like, what is a capacitor, and where one can use these capacitors. And I also gave a brief idea about how a capacitor works and how one can charge a capacitor, discharge a capacitor, etc. And then I discussed about fuel cell. And fuel cell is a device which we probably do not see routinely, but this is another storage device which are coming up and extremely important. So today we will discuss supercapacitor. So I just add this word super with capacitor. So that means the supercapacitor has some importance or has some added properties which a general the dielectric capacitor doesn't have. If we just recollect that the resonance plot what we have discussed in the previous lecture, where we have seen a capacitor is a device which is having higher power density but less energy density. And then battery is a device which is having less power density and higher energy density. The supercapacitor is a device which is designed with the idea of capacitor but having higher energy density. So something like that supercapacitor a sort of bridges the capacitor and battery. So that means it is having higher power density but just less than capacitor, and it is having higher energy density more than capacitor but just less than battery. Okay. So that in one particular device we combine both the properties of capacitors and battery. Now the question is, why supercapacitor is important? So in principle what supercapacitor does, as I mentioned, it actually reduces the thickness of the dielectric layer or the active layer, and also with an enhanced area it gives high energy density. I'll come back to this point why we have to increase the area, effective area of a capacitor and make it a supercapacitor, and also reduce the thickness of the dielectric layer. But if one can do it, one can really get a capacitor with high energy density, and that is called supercapacitor. But as I just now I mentioned that its energy density is less than battery. But there are some other features which keep supercapacitors much ahead of battery. So what are these? I will discuss it detail later, but just for our information, the supercapacitor is a device or storage device which is having very good reliability. That means you can use it for long duration, which you cannot use for battery, normal battery. We all know, we all work with battery, and we all know that how many days or how many years you use battery. Okay, in your laboratory when you use a UPS, or at home when you use inverter, every year or in 2 years or 3 years you have to change all the batteries. Okay, if you do not do it, then these instruments do not work. So as far as the utilization of a device for a long duration, supercapacitors are ahead of battery. And second is they are environment friendly. Okay. So this is the basic objective of supercapacitor. So with this objective, I will just come to some points where we will discuss that who actually discovered the supercapacitor on when it is started. So if you go back to the literature, you will see that it was first patented in 1957 by GE Electronics. Okay. So the concept supercapacitor was first reported by GE Electronics, and then Soyo Corporation actually patented a device, full complete device, supercapacitor device during 1960, 1970. Okay. And then further it was developed by NEC, by Panasonic, that is in Japan, by Icon in Russia, and many other companies around the world. And at slightly later stage, Maxwell developed the supercapacitor with quite a high, the energy density. Okay, and it was reported, it was commercialized, and many people have used this supercapacitor, and these are all these supercapacitors are still under use. Okay, and they have a huge program in 1990 about supercapacitor program or ultra capacitor program, and under this program all these storage devices were developed. Okay. And in Europe, there is a company called Bestcap, nowadays we are known as Blue Solution. They make these products, and therefore the supercapacitors are in commercial use. Okay. But there are quite a few interesting aspects of supercapacitor, as we will discuss, which demand lot of research till date. And with the advancement of nanoscale material, there are a lot of promises of supercapacitor. Okay, so we will discuss the advanced material at later stage and how they are useful to design a very good supercapacitor. But before I discuss supercapacitor, let me again come back to the point of what is known as energy density or energy of a capacitor. Okay. So if you just look at this, the energy density of a capacitor is actually, it is defined as this amount of energy of a capacitor or any system per unit volume. Okay. And then generally it is represented by a quantity half epsilon E square. This is actually an electric energy density in a vacuum. Okay. So if we study electrostatics, we will see that, but in particularly in capacitor, what we do, how do we define energy density? It's simple. So if I consider just a simple capacitor or what is known as parallel plate capacitor, so these are two plates of a capacitor. This is the distance between the two plates. So this is metal plate and its area is A, and this is another metal plate is also having area A. Okay. So suppose there is no dielectric in that, only we have vacuum or air as a dielectric, and this is a potential difference between these two plates. Okay. So I have a charge plus Q here and minus Q here. Alright, so this is typical design of a parallel plate capacitor, and as I mentioned, and as all of you know, that there are various capacitors of various geometries, but for simple parallel plate capacitor, you can have the energy is equal to half CV square. Okay, this is well known. Alright, and so what is this energy? If we just look at this capacitor again, with slightly different drawing. So I have a positive plate, I have a negative plate, I have a supply connected here. This is the positive terminal of a battery, this is the negative terminal of a battery. Okay, and in between I have at this moment we have air, and then there is an electric field here. Okay, so this is electric field E. All right. So this is the way we store energy in the capacitor. So what is this energy? It is nothing but an electrostatic energy. Okay, in terms of electric field, a potential energy is stored, which is electrostatic energy. Okay, so let me just complete this. So energy of a capacitor, we know if the potential difference is V and capacitance C, then it is half CV square. And if I write energy density, and I represent it by say ED, energy density is equal to half CV squared by A into D. A is the area as I mentioned, and D is the distance between the two plates. Okay. So now if we just little bit of simplify this equation, so we all know that capacitance of a capacitor, okay, is equal to charge by voltage. Okay, and this for a parallel plate capacitor, it can be written as epsilon naught A by D, and the field is equal to V by D. Okay, so this gives me an expression for energy density U, which is equal to half epsilon naught E square. This is a very important physical quantity of a capacitor. Okay, the energy density. That how to increase this energy density. Because if you look at the Ragon's plot, capacitors are having very low energy density. Okay, although they have very good, very high power density, but energy density is quite low. So how to increase the energy density? In order to increase the energy density, we have to, design it in such a way so that we have higher effective area and lower, the dielectric, separation or thickness, so that I can have a higher capacitance. If I have a higher capacitance, then I have higher energy density, and that is the idea of supercapacitor. So we have to understand the basics of a supercapacitor, how it is done. So the points which we should note, the important point is that what is requirement, we need to increase the capacitance. So in order to increase the capacitance, we have to increase this effective area, okay, of the capacitor plates, and then we have to decrease the separation or the layer thickness. Okay, and in order to do this, we have to make a little bit of redesigning of capacitor. Okay, the kind of design which we have for normal capacitor that I have drawn needs a little bit of modification, and that is called supercapacitor. And if it is possible, then we can make a capacitor with high energy density. Okay, they are also known as electrochemical capacitor. So how people do it? Again, you have, two plates, same as capacitor. They are known as collectors. So this is a collector and this is another collector. Okay. So now what I will do, I will put some sort of, carbon based material as an electrode here. They are like carbon electrode. Let me tell. There are various allotropes of carbon which are used, that I will come later, but they are carbon electrodes. Okay. So now here, so suppose if this is positive and this is negative, so I have positive charges here and negative charges here. Okay, and in between I have a separator and then I have electrolyte. Now you see what happened. Okay, so now as soon as you apply a voltage, there will be a movement of the charge carriers. Okay, because the whatever solution you use as an electrolyte, there will be separate charges will be separated, and according to their polarity they will go to the respective plates, okay, across the membrane, and then they will physically adsorb very close to the carbon electrode. Okay, so what will happen, that near this carbon electrode I will have a sheath of negative electron, negative charge, and close to this electrode I have a sheath of positive charges. So if you look at very carefully what is happening here, it actually reduces the layer thickness and it forms here, it is a layer which you call a layer between the electrolyte and the electrode interface, and there is another layer in another electrode in electrolyte interface. Okay, so they are actually known as electrical double layer. And this is the first design of a supercapacitor. We will see there are other supercapacitor also. This very specific name of this particular supercapacitor is electrical double layer capacitor, EDLC. Okay. So, but while doing this particular, the mechanism or the design of the modification of the design of the capacitor, what we have done is basically we have reduced the layer. So earlier the dielectric was completely in between the two plates in a supercapacitor in a capacitor, and we used to just take the distance between these two, just the physical distance between the two plates, or the thickness of the dielectric slab, that is the D. And now I made by this particular physical, introducing this particular physical process, I have created electrical double layer whose thickness is very small. So we reduce the thickness. Okay. So D is reduced. And now the question is, another point is how to increase the area, effective area. Effective area can be increased by the modifying the material properties of this double layer. So I can have different carbon based materials, okay, which are having different properties. Suppose there are many carbon based material which are having different pores, okay, or I can make it very small sized material, so that if you remember, we have discussed in detail in many times that if I reduce the dimension, then I have actually high surface to volume ratio, and that actually increases the area. Eventually both these modification enhances the capacitance and the energy density. Okay, so this is a most important the property of a supercapacitor, or this is the motivation behind designing a supercapacitor. So now let us just look at what are the important features of a supercapacitor. So when we design this particular the device, what are the advantages we get? The first advantage is it stores high amount of energy. So when we talk about high amount of energy, what we mean that it stores more energy as compared to a normal capacitor which we use, much more energy. Okay, because now it is clear, because I increase the capacitance. Okay, if I increase the capacitance, the energy will be increased. Okay, so half CV square will be enhanced. So I can have a good energy storage or higher energy density. Have high capacitance, this I have already discussed. Okay, in the light of parallel plate, you have, if the surface area is enhanced and the layer thickness is reduced, I have higher capacitance. There is very important property that is called high rates of charge and discharge. Okay, what does it mean? It means that, suppose I compare a battery with a capacitor. So what is the difference? Go back to the Ragonet's plot. We know that battery is having a device, a storage device which is having higher energy density, and capacitor is another storage device which is having higher power density. Why it is so? Because battery, if you charge, it takes lot of time to discharge. Okay, and that is the reason the power density of battery is low. But if you go back to a capacitor, you can very easily discharge the capacitor. You can hold high amount of charge and you can very rapidly discharge it. Okay, so you have a very good charge and discharge cycle, and that is quite optimized in case of supercapacitor. So you still maintain a high rate of charge and discharge in the supercapacitor, and compare it with battery, it is much better. Now, as I mentioned, that durability. Okay, So it actually has very little degradation over a long time. Okay, so that means its lifetime is much better in as compared to a battery. Okay, and it is having low toxicity. Battery, we all know that the chemicals are so toxic. Anyway, later we will discuss battery in this particular module, and we will see there are a lot of change in the material of the battery also. But as far as the batteries which we use, we are always careful that they are toxic, they are not environment friendly. But supercapacitor doesn't have this problem, and it is also having high cycle efficiency. So when we talk about a cycle means we charge a device, suppose a capacitor, we discharge it, and there is some period in between. So the entire charging and discharging process makes a cycle. And when we talk about supercapacitor, it is having a very high, the cycle efficiency, almost 90 to 95%. So these are very important features of supercapacitor, which usually makes a demand in the market. Now I compare with a battery, very well known battery, that is lead acid battery. So all the parameters, let us look at a lead acid battery and a standard supercapacitor. So if you look at, so first thing is specific energy, which we also call energy density. The unit of this is watt hour per kilogram, and this is 10 to 100 in case of lead acid battery, and for supercapacitor it is low, 1 to 10. So that means energy density is lower in case of a supercapacitor. Come to specific power density, which is defined in watt per kilogram. So in this case, lead acid battery, the this is less than 1000, but if I come to supercapacitor, it is higher, okay, less than 10,000 or close to 10,000. So that means supercapacitor, we gain a power density. Okay, if I consider now the cycle life, as just now I mentioned, in case of lead acid battery, typically the cycle life is the 1000, and in supercapacitor cycle life is much higher. Okay, and that is extremely important. It is almost 50,000 or more. So this is the second advantage of a supercapacitor. And charge and discharge efficiency, a typical lead acid battery is having 70 to 85%, but a supercapacitor it is 85 to 98%. So this is the third advantage of supercapacitor. Now if I look at the charge duration or charging duration, that is typically for battery 1 to 5 hours, but a supercapacitor it is much faster, 0.3 to 30 seconds. Okay, so that means the charging is very faster, and which is required. So there is another advantage. And then the discharge duration for a battery is 0.3 to 3 hour typically, but in case of supercapacitor it is 0.3 to 30 seconds. Okay, so that is also very good because it is very fast, and therefore it is having very good power density. If I consider shelf life, then battery is in years, it is 5 to 15 years. Okay, but for supercapacitor it is more, 20 years, depending upon different batteries. Okay, some battery shelf life is even less. Okay, but supercapacitor shelf life is much higher. But if I consider the cost, battery is slightly better, it is slightly lower cost, and supercapacitor is having medium range cost if I consider all the storage devices. So in terms of cost, supercapacitor is a little bit costly, but if I look at the parameter like safety and nature friendly, battery's performance is low, supercapacitor is medium, and then operation temperature, battery is -5 to 40, supercapacitor -40 to 75 degrees centigrade. So you can see in most of these, the parameters, when we look at or the features of these two storage devices, a battery and a supercapacitor, it seems that supercapacitors are better, and therefore the the economy or the market is driving towards the supercapacitor. So some research is required so that we can design material, we can design supercapacitor with relatively lower cost, okay, but with higher efficiency and better application in different appliances. Okay, fine. So these are the advantages of supercapacitor, and now let us see what are the different supercapacitors that people have designed and fabricated, and they are in use presently. So if I just look at the supercapacitor, there are three types of supercapacitor. The first supercapacitor is EDLC, as I mentioned just now. So this is the first supercapacitor. The second is pseudocapacitor, okay, and the third one is hybrid capacitor. These are the three supercapacitor. So how they are different? Just now I discussed about a basic construction of a supercapacitor, which is nothing but a EDLC. So how does it work? It works completely based on physical process. Okay. So what are the physical process? It is based on adsorption or desorption process. That means when ions move from electrolyte and it move towards the electrodes, there is no chemical reaction, or you can say there is no Faradic, process. So when we talk about Faradic process, we mean that there is a redox reaction, that is reduction and oxidation reaction, which is not there in case of EDLs. It works in terms of a physical process, physical adsorption and desorption of electrolytic ions in the electrode. Okay. And second is pseudocapacitor. Pseudocapacitor actually works on the basis of Faradic effect. Okay, so there is a chemical reaction involved in that. Okay, there is oxidation reaction. There are other chemical processes also. There are certain advantage of non-Faradic like EDLC and Faradic like pseudocapacitor. But if one combines both the processes, suppose in one particular structure or one particular device, I want to combine both the processes, that means non-Faradic like EDLC and Faradic like pseudocapacitor, then one can get what is known as hybrid capacitor. Okay. So we have to remember these three types of capacitor, and today I am just going to give you very briefly the idea of all these three capacitors, how they work and what are the advantages, disadvantages. Now the first one is EDLC. So I have already discussed about the EDLC in my first discussion on supercapacitor, when I discussed the basic properties of a supercapacitor. Now if we typically look at EDLC, it is actually a supercapacitor. As I mentioned, it works on the basis of non-Faradic process. You can say there is no chemical processes. So how it is possible? It actually depends on what electrode you are choosing, depending upon the electrodes which you choose. So depending upon the electrode, there are three types of EDLCs. So if I write here EDLC, one is activated carbon, as an electrode. Second is carbon aerogel as an electrode, and third is carbon nanotube. This I am talking that when people just started working with this particular supercapacitor. There are a lot of modification of the material at later stage, which we will discuss in the last part of this lecture. But let us just start with what are the basic electrode material that people have used, okay, in EDLC. So again, recollecting how does it work, that it actually works on the basis of the double layer formation, electrical double layer formation, and as I have shown that these carbon electrodes are very closely spaced with the collectors. Okay, different charges are induced in the electrodes, and accordingly there is a driving of the charges which are being, or the ions which are being generated in the electrolyte, and the movement of the ions takes place accordingly. Okay. So one thing is that these electrodes are designed in such a way, these carbon based material electrodes are designed in such a way there is hardly any recombination takes place in that. Okay. So what happened that all these ions which go from the electrolyte to the respective electrodes are physically absorbed. All right. So adsorption process depends on the property of the electrode material, that is carbon material. And that again depends on what are the pore sizes of the network which is used in the electrode material. And these are the important. So depending upon that, as I mentioned, there are three types of the electrode. The first one is activated carbon electrode. So what is actually activated carbon? Activated carbon is basically, it is produced from carbon only. Okay, it is called activated because it is a sort of thermal activation is done. Okay, it's a mechanical activation is done on the activated carbon, and this activated carbon, the typical morphology of activated carbon you can see here, and this one can use as an electrode. Okay. So why you can use it as an electrode? Because there are a lot of pores in this activated carbon. So typically, if we remember that we have micro or nanopore when pore diameter is typically 20 angstrom to say, typically it is 50 angstrom range. Okay. So I can have a mesopore also, which is typically 50 angstrom to say 500 angstrom range, or I have micropore, which is typically, or I can say greater than 500 angstrom pore size. So what are the advantage when we use activated carbon as an electric material? You have a distribution of pores. Okay, depending upon how you have fabricated this activated carbon. So when I have distribution of pores, that means I have a different area consideration. Okay. So suppose I have all are very small pores, a nanopore. So my effective area, that means we again go back to surface to volume ratio. It is more when I have more smaller pores, nanopores or micropores. Okay. And if I have say all are say micropore, uh, sorry, not micropore. Please let me make a correction here. It is macropore, not the micropore. This is macropore. Macropore means the pores are more than 500 angstrom size. Okay. So that means I am having higher sizes. So higher size means I have less surface to volume ratio. All right. So where I get a better area, I get a better area when I consider micro or nanopore activated carbon, or where I have less area when I have a macropore activated carbon, and where I have an intermediate area when I have a mesopore or mesoporous activated carbon. So now when we synthesize this activated carbon, it is very difficult to control that all pores should be of this size. There is a distribution of sizes. It could be dominated by micropore or nanopore. It can be dominated by other pore sizes also. Okay. But whatever it may be, if I am having smaller pore sizes, then what I get an enhancement in area. Okay. So I already have a electric double layer configuration. I already have a less, the layer thickness that is already there as per the design of the supercapacitor. Okay. But an extra added thing is that just by introducing the ports and controlling the port size, I am having higher area, and this eventually gives a higher capacitance. All right. So if I have a higher capacitance, okay, I have a higher energy density. Okay. So now I will come to a very important quantity. So we have sort of analyzed that we are having a higher energy density, and now we will look at what is the power density. Okay. So how one can see that the enhancement in power density. In order to enhance the power density, what is required is the power, okay, P, it is defined as the voltage between these two electrodes divided by ESR. ESR stands for equivalent power series resistance. Okay, what is the meaning of equivalent series resistance? This actually there is a quantity 4 is also here. If you the work out this power density, you can get, or power of a capacitor, you can get this number. But the important thing is that it depends on the voltage, and the voltage is fixed. It depends critically on ESR. Okay, equivalent series resistance. So ESR stands for equivalent series resistance. When I talk about equivalent series resistance, what physically we mean? So physically we mean that if I again look back to our design of the supercapacitor, so I have two electrodes here, okay. I have, suppose the activated carbons are here, and then there is a charge double layer formation. This is separator, okay. All right. So in this, when I consider the equivalent series resistance, it is basically resistance which is connected in series. This resistance connected in series plus all the resistances which are accounted in this particular configuration, like the resistance of the plates, resistance of the collector, okay, resistance of the medium. So if I consider all the resistances, then it makes the equivalent series resistance. So remember that what we need here in order to enhance the power density, in order to enhance the power density, I have to reduce the equivalent series resistance. So what is the design motivation of a supercapacitor in general or EDLC or other supercapacitor? I have to enhance the energy density, okay, by enhancing the capacitance, and I have to enhance the power density also by reducing the ESR, okay. But that also very critically depends on the port sizes. So people have done lot of theoretical model with different port size and looking at what is the energy density and what is the power density, and they came to a conclusion that if the port sizes are smaller, just now as I mentioned, if it is having lot of micropore or nanopore, then it is having higher energy density, okay. And if the port sizes are larger, then it is having less energy density but higher power density. So this is what the theoretical model tells us. So therefore, we have some sort of optimization when we make activated carbon as an electrode, okay. So this is the first electrode which people have worked on for an EDLC, and the second electrode is carbon aerogel electrode, okay. So what is carbon aerogel? It is like other organic gel only. So a kind of organic gel which you do a sort of carbonization process and you make a carbon aerogel, and you can see this is a typical morphology of a carbon aerogel. That means I have a very controlled amount of pores in carbon aerogels also, but having extra advantages that it is having lightweight, it is highly porous, it is low electrical resistivity, possesses large surface area, okay. So low electrical resistivity, that means I have a reduced ESR. So if I have a reduced ESR, I have a higher power density, and if the surface area is more, that means if A is large, then I am having higher capacitance, that means I am having higher energy density. So you can make a kind of balance in case of carbon aerogels, okay. But what people have seen that these materials are sometimes not very stable and they do not show a very good cycle life, okay. However, there are certain advantages of using carbon aerogels. In later stage, people have used another material which is very common now, and lot of research work is going on in supercapacitor, that means using carbon nanotube. So you can see this carbon nanotube morphology. So what is a carbon nanotube? You know, carbon nanotube is basically an allotrope of carbon, where if you just consider a two-dimensional graphite, or which is popularly known as graphene, and you roll it, okay, you make a roll of two-dimensional graphite, so it becomes a small cylinder, okay, of typical diameter, say 1, 2, 3, 4 nanometer, very small diameter, okay, something like this, a cylinder. When you roll, okay, so typical diameter is 1 to 3 nanometer, and the graphite is rolled. All the two-dimensional graphite is, or graphene is rolled, okay. Now this rolled tube, okay, they can make a sort of network, three-dimensional network, because their length are more, micron length, but with very small, you know, the diameter. So that is carbon nanotube. And we have different carbon nanotube like multi-walled carbon nanotube, where there are, you know, one nanotube is within another nanotube, okay. And this could be a single wall nanotube where there is only one wall which can define a nanotube, okay. But the advantage is that with this nanotube structure, what you make is an entangled 3D network. You can see the morphology. This morphology itself shows that you have an entanglement of carbon nanotubes. Okay, they are entangled with one another and they make a a 3D network. What are the advantages of that? The advantages of this is that it can absorb the ions from the electrolyte very efficiently. Okay, this is the first advantage. Second is, as the nanotube, okay, there is an extra path of transport of charges also. Charges should be absorbed and they should be transported also, and the transport is very good. So in case of the pore structured which electrode which I just now I have discussed, in those cases where the the ions are getting absorbed, okay, but sometimes they are free also because the ionic diameter is much more than the pore diameter and they are not efficiently even absorbed, okay, and they are not being even transported. But here you do not have this problem. So I can have a very good transport path. That means I can have a lower resistance, so I can reduce ESR, increase the power density, and as it is a 3D network or mesh kind of structure, it is having higher area, higher capacitance, and higher energy density. So that means it seems that carbon nanotubes are actually the material which can solve the purpose of what we look at the future generation supercapacitor. Okay. All right. So now I will just very briefly discuss the two other supercapacitors. I have already mentioned that there are three supercapacitor. One is EDLC, which we have discussed, and another is CO2 capacitor. If we look at CO2 capacitors are also, depending upon the what electrode we are using, CO2 capacitors are having one conducting polymer type electrode. So what is conducting polymer? This is also very interesting the material in polymer science, this is, or material science. There are some conducting polymers like polyacetylene, PA, polyaniline, or called PANI, polypyrrole. Okay, there are several examples, polythiophene or PTH. They are the conducting polymer. So what is conducting polymer? They are polymer, but they are having a very good conductivity, okay, without added any conductive agent in that. So then they themselves are conducting. Okay, so if you have a good conducting polymer, you reduce the ESR. Okay, you enhance it. But now the function is different. Okay, in pseudocapacitor, it is completely Faradic process, as I mentioned. So what are the processes that are going on in pseudocapacitor with say one kind of electrode like conducting polymer? The processes are say electrosorption, then redox. Okay, so these are the two important chemical processes which are going on in case of pseudo capacitors. Okay, rest all other processes are fine. So you have a thin layer of dielectric, and then you have a low electro equivalence series resistance having higher power density and also higher energy density. Now the question is, people also look at two types of conducting polymer, making an N junction and P type, and they want to modify the the properties of this type of pseudocapacitor. However, there are not very good success in that because the designing of an N-type conducting polymer is an issue. Okay, and there is another disadvantage with this type of supercapacitor is having, it is having less cycle life. Okay, so what are the next the pseudocapacitor which people have worked with? These are metal oxide. Out of different metal oxide, the ruthenium dioxide is one material which is used in the pseudocapacitor design significantly. What is ruthenium dioxide? The ruthenium dioxide is having very high conductivity, with ruthenium sitting here, and there are 6 oxygen atoms which are connected with this ruthenium, making an octahedra. Okay, it is having higher conductivity, therefore it is having very high power density. Okay, and also if you can reduce the layer thickness and if you have efficient transport process, you can have a higher energy density in this pseudocapacitor. Okay, so I discussed both this EDLC and pseudocapacitor, and now we will just briefly tell about the hybrid capacitor. So what is hybrid capacitor? Hybrid capacitors are the capacitors where you add both EDLC, sort of you that means you add the non-Faradic process of EDLC and you also add the Faradic process of pseudocapacitor. How one can do it? It is simple because you have to make a composite. Okay, so in the composite means you make a composite of say an activated carbon plus say conducting polymer composite. Okay, you make N type, as I mentioned just now, N and P type conducting polymer. People have done research, and at least theoretical model tells that they are very good, efficient and high energy density. But if you don't go by this, both N and P type conducting polymer, one particular the type you keep is the activated carbon, and another you make P type say conducting polymer. Okay, then you have both the advantages. So what are the advantages for activated carbon? You have these physical processes which are going on depending upon what are the pore sizes, and then for conducting polymer you have the Faradic process which are going on. Okay, so you combine non-Faradic and Faradic process, and depending upon how good transport in your hybrid mode of these two material, depending upon how much the equivalent series resistance are lowered, the power density and energy density both are increased in case of hybrid capacitor. So I have the advantage of enhancement of both energy density and power density. People also these days talk about battery type hybrid supercapacitor. Why they are battery type? The one electrode they use a typical battery material like sodium hydroxide, okay, lead oxide, and there are various other materials which are used in battery, as I have discussed in the last class. And another they use it say the conducting polymer. Okay, so there is a very nice design that is called battery type. One was composite type and another is battery type hybrid, where you can have a highly optimized energy density as well as power density. Okay, so these are all design of supercapacitors, and in the next class I will just see very briefly how to model a supercapacitor. But let me summarize what we have discussed today, the important points. So I first discussed how to calculate the energy of a capacitor, energy density of a capacitor from a very simple parallel plate capacitor configuration, and then I discussed about what are the basics of a supercapacitor and what are its important features, how to compare a supercapacitor and a battery, and what are the added advantages or added properties of a supercapacitor which can keep it slightly ahead of battery. And then I discussed three important supercapacitor. One is EDLC and its different electrodes. I discussed pseudocapacitors, which is a Faradic capacitor, okay, and its different electrodes. And finally, I introduced hybrid capacitor, where both Faradic and non-Faradic processes are going on, making a very highly efficient capacitor, okay, with good lifetime good cycle efficiency and also high energy density and power density, which demands lot of application in various appliances. Okay, thank you.